eventually, with Elizabeth Rauscher, we wrote a paper. This is the title of the paper, The Origin of Spin, a consideration of torque and Coriolis forces in Einstein field equations and grand unification theory. This is a paper that's in peer review right now. As a result of what I'm talking to you about, this is a new solution to Einstein field equations. Okay? There was a solution that was given to Einstein field equation after Karl-Schwarzschild. It took a very long time. It wasn't given until 1965. In 1965, the Kerr and Newman solution was rendered, in which you had a black hole, or the object was allowed to spin and have charge. So it had spin, angular momentum, and charge. And it took all the way from Einstein writing these equations to 1965 before that was able to be figured out. So you can imagine the complexity, and this is basically the solution that's mostly used to interpret what we see around stars, black holes, galaxies, and all this. There's a problem though. When you take these solutions and you apply them, for instance, to a galaxy or to the universal size, the result of the equation does not match observation. Okay? The result of the equation only predicts 4% of what we see out there. Alright? That is, in order for the universe to look the way it does, or for a galaxy to look the way it does, with the amount of mass that we are seeing in that galaxy or in the universe, and when we put it in the Einstein field equation, it doesn't match. What they have to do, and what they've done, which I believe is a complete cop-out, is that they've added the 98 or 96% of the mass that's missing and the energy that's missing. They called it dark matter and dark energy. It's very, very convenient. Instead of revising the equation, they assume that it's something out there that they cannot measure and that they cannot see. So that's very convenient, because who can tell them it's wrong? Right? They've been looking for dark matter and dark energy since then. I mean, it's been, almost, at least 10 years of, funding and detectors and all sorts of experiments to detect dark matter and dark energy. Now, I think they will detect something. However, I don't think it's going to be what they think it is. I think the error is in the equation. And the error in the equation is describing, if this error would be corrected, would describe something that's out there, but that's not dark matter or dark energy. It's only a force that allows these dynamics to happen. And that force, I realized, had been omitted. And I'm going to show you how I found that out. I studied the Kerr-Newman solution that had finally added rotation into the space-time, so that if an object was rotating, they could calculate that as well. The thing is when they did so, they wanted to get rid of complexity as well. Because angular momentum and gyroscopic effects are so complex, they did something very strange. They decided to eliminate the gyroscopic effects of rotation, like eliminating Coriolis forces and torque and things like precession and all this. Well, how would you do that? Well, the way they did this is that they attached the frame of reference to the rotating metric. so that there would be no force. Now, this is a little trick that's used in physics and that really tweaks the results. And because this is buried under enormous amount of complexity and very little people on this planet understand these complexities, it is not being noticed until now. Now, what they did is this. Imagine this. You've got a shaft that's turning, maybe on the lathe here, right? Or maybe there's a V8 motor spinning this shaft, right? And it's spinning at 5,000 RPM and you're in front of it. And in a moment of illumination or in a moment of extreme stupidity, you grab onto that shaft. All right? With all your might. Well, you're going to experience some effects. Okay? Those effects have to do with shearing, like your skin flying off, heating, like smoke coming off your fingers, all sorts of effects like this that are certainly uncomfortable and that have to do with the force of torque applied now to your hands, right? That's forcing that shaft to spin. All the 300 horsepower of that V8 motor is spinning that shaft. Well, if I grabbed you at the exact moment that you went to grab that shaft, if I grabbed you on your center of gravity and spinned you at the exact same rate, you would feel no force. You would feel no effects in your hand. It would be stationary relative to you. You see? However, I could still say that I'm accounting for angular momentum because I could count the turns that you're going around. So I would have a frequency rate of angular momentum. You see? And that's what they did. Why did they do this way? It actually goes all the way back to a fundamental assumption that was made. That things are spinning in a frictionless environment forever. That is, the assumption is, because if you ask a physicist, what is making the Earth spin? They'll tell you it's because it's in the solar system that's spinning. And you say, well, what's making the solar system spin? They say, well, it's in the galaxy that's spinning. Well, what's making that spin? Well, that's in the supercluster. Well, what's making that spin? Well, that all started in the Big Bang. You see, son, if it had the Big Bang... Sorry, I'm being cheeky. There was the Big Bang, and then all the energy through everything spinning, and it's been spinning in a frictionless environment since then. So we don't have to account for spin because it's inherent to the Big Bang. First of all, that doesn't tell you where the energy came from to generate that moment of impulse, but certainly it's a very, very large generalization because when you look around, we just happen not to be in a frictionless environment. I mean, it's the same thing at the atomic level. They tell you that electrons spin perpetually because of being in a frictionless environment. They got spinning at the Big Bang and they're still spinning now at 99.9 something the speed of light, right? Those electrons. Now that's a lot of spin for a long time. And when you look out there, it just happens that it would be true if there's only one atom in the universe. But as soon as you have two atoms, now you have interacting fields. You have friction, you have collision, you have all sorts of things happening. Gravitational fields acting on each other. Not only that, in order for that statement to be true, then all objects would have to be solid, true and true, homogeneous, which we know they're not. For instance, the layers of the sun rotate at different rates and have huge amount of frictions between them. Think of the inside of the Earth. Is the inside of the Earth spinning in a frictionless environment? I don't think so. It's spinning at a different rate as the surface, obviously because we're getting a magnetic field resulting from a dynamo effect. So what's making the inside dynamo spin against the mantle? You're talking molten lava, not frictionless. Not frictionless at all. Solar winds in our solar system, the gravitational pull of the Earth. You see, here I have 2 eggs. And don't worry, I'm not going to throw them at you guys. That would be a first. Eh? The presenter throws eggs. Bad crowd. Here I have a hard-boiled egg. Fairly, constant density through and through. Okay? Here, an unboiled egg. High level of viscosity in the middle. Okay? I'm going to spin the hard-boiled egg on the floor. Now imagine this hard-boiled egg was in a frictionless environment, or a very low friction environment. It could spin, oops, let me try that again. It could spin constantly and homogeneously as it does here and slow down, but that's mostly because of friction on the floor, right? Now let's imagine that it was frictionless, but now you could see how that could be possible. But now let's try to spin an egg that has high viscosity at its core. It stops very quickly. Most of the angular momentum is absorbed by the viscosity of the central core of the egg. Galaxies are just like a non-boiled egg. It has all sorts of density, plasma density change, all sorts of friction, and all sorts of different levels of viscosity, and so is the center of the Earth. There is actually currently no appropriate geological description on how the moment of inertia of our inner core of the Earth occur. How do we get a magnetic field, and what's spinning that dynamo in the center of the Earth? Did you guys have bicycles when you were kids that had those little dynamo on the wheel that created enough current to put up a light in front so you could see at night? Well, in order to spin the dynamo, you still have to pedal. So there's got to be somebody pedaling. There's got to be something forcing things to spin.